Hi everyone, welcome back to another Calculus 12 video. Today we're doing 7.4, Applications of Trig Functions. And basically it's no new concepts, but it's applying the stuff that we have already learned in this chapter. So I'm just going to go through one example with you, and that should be enough because nothing is really going to change. It's just different sentences, and it'll be your job to read through those sentences and translate them into equations. And I do find one of the best ways to do that is to draw some drawings to help you to organize the information. So you take a look at this first one. It says, what is the largest length pipe that could successfully be carried? I'm going to do this. Largest length pipe that could be successfully carried around a corner if the hallway widths are 1.5 meters and 2 meters wide. Okay, so I don't know if you can visualize or picture this, but if we're looking for a pipe that's going around a corner, if you can picture that like in a hallway somewhere, or yeah, hopefully you have a mental image of what that looks like. But let's start by just quickly drawing it out. So if it's a corner, I know it's going to be something like that. Maybe I'm going to make that one like this wide, and that could be the 1.5, and this one will be a bit wider and make it the 2. So I know that it's something like this, and then I know if I'm looking for like the largest length pipe, maybe I'm going to call that L, and this would be our L. I don't know if I need to mark it there, if I've done it in blue. So that's what it would look like. And this is a unit in trigonometry, or a chapter in trigonometry. I know I'm using my trig skills to help figure this out, and the other clue to give that away is the fact that, okay, clearly we have a 90-degree angle there, and we know trig has to do with 90-degree angle triangles. So I'm sort of keeping that in mind, or using that to help guide me with where to go with this. So, knowing that, sifting my way through the information, I would be finding ways to, like, we're basically trying to figure out the length of this blue part here. And the only information that we know, if we look at it, is that one of the widths is 1.5. I'm going to do that here. 1.5 meters. So I know that if I draw like another line there, that makes another 90-degree angle, and I know that this side would be 1.5. Okay, so there's that part, and then I'm going to call this down here theta. And then I'm going to do the same thing over here. If I were to go through here and draw this out, I know that this length here is 2 meters. I didn't put the meters by the 1.5, but I don't have much room there. So know that it is 1.5 meters. I'm just leaving it off the diagram. And I could also do this. So if I know that that's 2 meters, actually, let me change this. I want to get them sort of together. So I'm going to do this. I'm going to do a dotted line there, which gives us my 90-degree angle. There's my theta down there. And then here, I know that it's 2, so, okay, fine, I'll draw meters in there, but know that I just don't have enough room, but we know the units. We can deal with the units after. So I have 2 right-angled triangles, and I've purposely done this so that the side of them, like, attaches to give us the largest length pipe, because this is what we're going to do with it. We want our pipe to be these 2, I'm going to do this so you can clearly see like which triangles I'm dealing with, but basically I'm going to call this L1. This is going to be L1, and if I do the same thing over here, I'm going to call that one L2 plus L2. So this is sort of giving me something to work with. I have L1 and L2. Okay, so then I want to put all this stuff together. I know I have my L1 and I know I have 2 meters, and then I stuck the theta in there. So I can actually rewrite this using my trig skills. So I know that L1, maybe I'll do this, would be equal to 2. So remember SOHCAHTOA, so it's like opposite over, sorry, I'm skipping a step here. I can say, let's go through it. Sine theta, if I look at theta, would be opposite over hypotenuse, which would give me a way to relate the 2 and the L1 together, which is what I'm trying to do. And then this is how I skipped a step. I want to isolate this for L1, so I could say that's like 2 over sine theta. So same thing, I've just rearranged my equation. I'm going to put a therefore symbol there. And I want to do the same thing with L2. Sorry, I don't want to put a plus there. I just want to rewrite this. So if I look at L2, I know that this time I have the adjacent side. That tells me I must use cosine equals adjacent, which is 1.5, over my L2. And just like this thing, I want to rewrite L2 isolated, so it's 1.5 over cosine theta. So to make it super clear, I'm just rearranging my equation to isolate the L2 that was at the bottom, because that's what this overall equation has to do with, and that's the one that we're interested in. So I can put this all together. L is equal to 2 over sine theta, so that helps me deal with that part, plus, oh, the color coding is awful, let me do this properly, plus 1.5 over cosine theta, which allows me to deal with that part. I'm really going to stress this. Take or leave yourself enough room to be able to work your way through it. I find oftentimes I see many of you cramming things in, and you know how to do the math, but you forget something or you leave something off. So allow space for you to be able to figure this out. But basically what we're doing here is we are trying to look at the length in terms of similarities. We're looking for common ground between them, which happens to be the theta. So actually maybe a better way for me to say this is L of theta, to tie that in, because that's what math is. We're looking for similarities and common ground. This is like metaphors for life. So I hope that so far that makes sense. And then if we are looking to maximize the amount of space, or max and min, remember those problems and that stuff that we did? So we know that we want to take the derivative of this. So if I want to do L prime of theta, so again, not necessarily something new. This is us practicing and applying the stuff that we've learned in this chapter. So I am just going to give you the derived answer to this, because I'm going to assume at this point you all are okay with pausing the video or doing what you need to ensure that you've got this, but over sine squared theta. So that deals with that part. Plus, we want to do the same thing with the other part here, which would be 1.5 sine theta over cos squared theta, because do you see in each case I am using the quotient rule in order to take the derivative of this. So again, if you're unsure, pause the video, make sure you know how to do it, and then work your way through. And then the rest of this, again, as usual, becomes a matter of, I'm confused with which color to use. Like, we set it equal to 0, and then we want to work our way through this stuff. So do you see that I would want to get the same or a common denominator here? I would do that by multiplying this by cos squared theta over cos squared theta, and multiplying this by sine squared theta over sine squared theta. I'm just quickly, roughly writing it out. You all know how to do that. And I'm going to tell you what we would get. When we do that, top and bottom, and isolate and put things together, I'm going to give you what we would get. We would get negative cos cubed theta plus 1.5 sine cubed theta all over sine squared theta cos squared theta. Again, hit pause if you want to. Make sure that you are okay with multiplying things top and bottom. It's pretty straightforward. I think you can see where it's coming from. But at this point, remember how we had set it equal to 0 here. So notice that if I'm taking all of this and multiplying by 0 up here, that would mean that the bottom just gets wiped out. So we're basically just left with, well, do you see that I could just take this and move it to the left side to make it positive? So I'd have 2 cos cubed theta equals 1.5 sine cubed theta. Okay, so I hope so far this is looking like it's easy to follow along with, or you get what I've done here. I just took that and used my algebra skills, moved it to the left. That left this remaining here. So at this point, I want to get like things together. So I'm going to do 2 over 1.5 on the left. And basically, I'm just crossing them. So I have sine cubed theta divided by, I divide this out on both sides. So cos cubed theta. So I'm just getting the numbers together on the left, the trig together on the right. And this is basically, well, 2 over 1.5 is like saying 2 over 3 over 2. So it's the same thing as saying 4 over 3. Again, if you need to pause and take a second and actually think your way through that, go for it. And this is like the same thing as saying sine theta over cos theta, but the whole thing cubed. And like, you don't need that step there, but I wanted to show you clearly where I'm going with this so that you understand, especially for those of you at home, so that you understand what just happened there and what I'm going to do next with this. So again, if algebra is all about opposites, then I would cube root both sides. So by cube rooting both sides, that would allow me to get rid of this. So I hope that so far that's making sense. That would mean that I have the cube root of 4 over 3 equals, do you see that sine theta over cos theta is just tan theta? So I'm pretty much there. Like, I've worked my way through and isolated things, and just to show you, if I want theta by itself, remember this, we would do inverse tan of what we had here, which was the cube root of 4 over 3. And you can punch that into your calculator. And when you punch it into your calculator, I've done this in degrees, and we would get 47.7 degrees for my theta. Okay, so see the potential for getting lost and not even knowing what on earth we were looking for. We were looking for L1 and L2, and I have a lovely equation here where I have this in terms of sine theta and cos theta. So I can use that equation and use what I just found for my theta. So I'm going to say L is equal to, and it was 2 over sine theta, so 2 over sine 47.7, plus 1.5 over cos theta, so cos 47.7. And you would want to punch this into your calculator, and when you do that, you would get 4.93 meters. So the largest length of the pipe that could fit through the hallway, but I don't need you to write all that, is 4.93 meters. I do want the sentence because the sentence indicates that yes, you were able to set up the equation, do the trig, derivatives, find the solution, and that you know and understand what it is you found instead of just plugging things into formulas. I hope that you found that helpful. I'm assigning you a few questions here to practice this, and I hope that you find that useful. If you're feeling up for a bit more, you can do 12 and 13, but I'm going to leave that up to you.